so let's begin with class.
Yeah.
So just update you a few things on the webpage. You know, this is where you should look to find all the information of the class. I've updated and added some emails for the TAs, so you can email them directly. So they'll mainly be the ones in charge of the homeworks. I'll probably limit my interaction to mainly clarifying things on the discussion group. If you haven't found it, you can get to it right here, or there's kind of a standalone interface. And there's been a bunch of questions already. Some of you have been asking some very good questions about that. So if you ask questions there, then, or you should look there before asking questions because they may have already been answered. And so if you didn't see, the first homework assignment is posted. And you have to first get approved to the group before you can post. This is so we can keep out some spam and stuff like that. So if you might want to post a question, you might as well go and request to be approved for the group. All right, so we're going to start the second topic of the class, which is going to be on similarities today. And we're going to get we're going to start again a little bit more abstract and high level, but we're going to get to some actual way you can model some action for real data sets. We're going to get into some of the nitty gritty of getting from some real data sets today about text and documents, and how to convert this into something that we're able to actually use some more high power techniques. Right, so so the theme of this section of the class is going to be similarity. And so the main idea here is you have two types of data sets. You want to know, how similar are they? So in many settings, actually, it's more common to talk about a distance between things. If you take a classic computational geometry, most of the discussion is based on some geometric distances, and we'll be talking about similarity instead. It's going to be a lot more convenient for the sort of things we're dealing with, so I just want to kind of break this down just to be completely clear on this. So if they're more, if some objects are more alike, then this is going to be large, where the distance is going to be small, right? So things are more similar if they're more alike, where distances they're further. If things are more alike, then the distance between them is small, right? So if we have a similarity between two objects A and B, then one way of converting it into a distance between A and B will be equals to 1 minus the similarity. So this is typically the case if this similarity is going to be in the range 0, 1. So this is a fairly common thing where if things are identical to each other, they're going to have a value 1. If they're completely different from each other, they're going to have a value 0. And then if you convert it to the distance, this distance will have, is then also going to be in 0, 1. And we'll talk about distances and more general types of distances later. And this is one way of converting them. Sometimes you want to convert from a similarity to a distance in a way that's different from this. There's some discussion of it in the notes. Okay, so we're going to look at these similarities where the more alike things are similar, and typically it's going to be in the range between 0 and 1. And so, we basically want to say, well, this is kind of a tautology, but like, so how similar are two objects, right? Are they close to each other? I haven't told you anything yet. But so for instance, if you have a set of customers, okay, so let's call this set A, and then if you have a new customer, we'll call this new customer Q. So this is like a query. I'll call it Q. Well, then we can ask questions like, is Q in A? Right. So is Q an element of A? So that means, are two things identical? So this is something you can check if you have something that exactly matches the properties of this customer. Okay, well, what's going to happen is that you're going to have people come back and you may not always be able to match things exactly. So you want to say, and this question is actually a lot easier than the next question. Is there a customer, let's call it A and A, such that the similarity between A and Q is less than some value delta. Right? So is there a customer in the set which is similar to your question? Right? So if you're taking pictures of people's faces, even if you have very similar lighting and the same pose, the two pictures are probably not going to be exactly the same, but they can be very similar to each other. You want to find, is there something similar from your query that's going to be in your set. So these are the sorts of things we're going to ask. And in order to do that, we need to define precisely different notions of similarity. So the sorts of things we'll be talking about today, we're going to focus on what's known as the Jaccard similarity. And so this is a similarity between sets. Okay, so we're going to have two sets. We're going to say how similar are the sets. And we'll talk about how you can use this to determine how similar two documents are. So two strings of text. We're going to take two strings of text and say how similar are these two strings of text. So this is a similarity between sets, and so it's often used for text. Okay, so what some of the uses for text? So say you have you're getting email, and you want to determine whether your email is this email coming in as spam, right? So it used to be that a lot of spam emails really looked identical, right? So they would send out, the spammers would send out all these emails which were exactly the same, advertising, something you could, some products you could buy on the internet or something. So that these were, but you could very easily mark one of these emails as spam, and then every identical email would also be marked as spam. So these spammers, so they figured out that they can't have exactly the same email. They had to modify the emails a little bit. And what you can do is you can take this text and you can break it down into these sets, and we'll discuss precisely how we do this. And we'll go through some examples. And then you can still tell if two emails are very similar to each other. So, spammers have gotten very good at this and figuring out how to break these sorts of distances, but we'll show a lot of additional techniques. This is also useful for determining the similarity between web pages. So now, when you search for a web page in Google, it'll try and return the first page will have 10, very different web pages. If you'd done this maybe 4 years ago, you may get several web pages which have almost the same content on. And in fact, there are certain kind of broader web pages like about.com that would find these texts, these web pages which are very useful, and then kind of copy the content. And so you would search for something and you have the original page and then the page from about.com, and then you might go to that page and you see ads and they make money. So Google now can detect if two web pages are very similar, and then it won't show you both of them. But it needs to be able to have a way of determining the similarity between it. So this is a very kind of simplistic view of it, but these sorts of techniques I'll talk about was actually some of the, we're actually using some of the very early search engines even before Google. They were actually developed, I think when they were developing the Alta Vista search engine. So then a third use of this may be if two students are working together on some homework assignments and decide, instead of turning in exactly the same homework, they want to say, well, I'm going to modify one a little bit, when they really should have been working together. Or they want to copy something off the web, and they turn that in. Well, if you don't modify it well enough, it's pretty easy to detect if it was basically a copy of something on the web. And there are websites where we can take a report or some code that you've turned in and put it through one of these tests and actually see how similar it is to other people's in the class. So don't try and cheat. You're not supposed to. So the ways I'm going to talk about are going to be some the fairly basic ways, and I'll talk about some of the variations of these. And to do these things well, you actually need to be very careful on how you choose these variations. And the choices should be dependent on the specific sort of problem and the sort of data you're looking at. And there's a general theme here, is that you're going to have some something like raw data, right? And so this could be like documents. This could be this could be customers. This could be web pages. This could be products. Okay, and we're getting this raw data, and this is in some format that may not be very convenient, not just the format how it's stored, but there's lots of extra information there. This may be, if this is a string of text, what do you do with it? If this is a set of attributes about the customers and they're not all the same, what we want to do is convert this into some abstract setting. So these could be things like sets. Points in RT. We'll talk about some other things like matrices and graphs later in class. And given one of these abstract types that you've converted this into, then you can use some very standard similarities, notions of similarity, notions of distance, and apply some very well-developed algorithms that we understand very well. And so a lot of the class will be doing two things. It'll be from here. So once you have this abstract setting, then you can apply some algorithms. So we'll be talking about some of these algorithms you can apply from these abstract settings, and we'll be talking about going from this raw data into these abstract settings. So here, this step
is mainly in modeling. Okay, you have some data in some format. You want to get it into one of these settings so that you can apply some known algorithms onto it. And there's a lot of choice here. There's no right way or there's no wrong way to do it. And oftentimes you have to try different things, or you need to use specific domain knowledge in doing this conversion. Okay, so today we'll be talking about going from documents into sets, and then we'll use the Jaccard distance, or the Jaccard similarity. We won't actually talk about how to compute this efficiently. It's going to look like a fairly inefficient thing to actually work with. On Monday, we'll talk about ways of how to work with this very efficiently. And this will build on some of the lectures from last week. Okay. So very briefly, so who knows what a set is? And who has not heard of a set? So everyone's heard of a set. So let's see. So then the Jaccard similarity. So is going to be between two sets, A and B, and this is defined as A intersection B over A union B. Okay. So this is pretty simple. So if you were to draw a picture here, so if this one, let me use some colors. So if this is set A, this is set B, then what this distance is going to look like is the intersection is the amount of stuff in here, and the union is A and B, right? So this is over the full union here. Okay. So sometimes it's useful to think of this being inside of both of these being inside of a larger set. This larger set is going to be kind of like the set N that we talked about, where you can think of them as all numbers between 1 and N, where N is some fairly large number. And the same here on the bottom. And so one nice thing about this, and we'll see more about this on Monday, is that this distance only depends on things which are in A and B. It does not depend on everything in the set. So if actually this is a very small percentage of the set, that's still okay. The distances, the similarity is not going to be something minuscule, even if A and B together are still very small compared to N. So just a small example so this is clear. So let's say A is 1, 2, 5, B is 1, 3, 4, 5, 6. Right, then A intersection B is going to be, and just so it's clear, the set notation, you have the curly brackets around the set of things. Then this intersection is going to be 1, 5, and this is the size of it, and the union, the size of the union is going to be 1, 2, 3, 4, 5, 6, and so this is going to be 2 over 6. So if you were to add another thing to set B, so the union gets bigger, but the intersection does not get bigger, then the similarity will be smaller. Then it would be, if you added a 7 here, this would be 2 over 7. Same if you added something to A that was not B, that would also be to 2 over 7. They become more dissimilar if you add something in one, not the other set. If you add something, if it had if 3 was also in set A, then this becomes 3 over 6, it becomes larger. So this conceptually makes sense. So there are other distances between sets. And if you look in the notes, I talk about a variety of them. And they're usually based on either the intersection, the union, or what's called the symmetric difference, which is the part in the union but not the intersection. So this part and this part together. And you can usually have a fraction of one over the other, and you can get a variety of different distances that have different properties. And I've defined some in the notes. And so it's, this one is fairly common to use and has worked fairly well on a lot of applications and is still in use in a lot of production software. Okay, so one of the other things you can think of doing is, instead of just looking at individual numbers here in a set, you could say that I'm going to first break down these numbers into clusters. One, okay, and then I'm just going to check whether I have an element of each cluster. Okay, so if these are different, if these are particular types of movies, for instance, or these each number corresponds to a certain movie, the clusters may be certain types of movies. So these could be action movies, these could be comedies, these could be horror movies, and you want to know, do certain people who are renting from Netflix, do they like certain types of movies? Because individual elements might not overlap as much as these certain sets, and it can be much more fine-grained than this. So then one thing you could do is check which customers are involved in which of the sets. So in this case, we'll call this a cluster. This one has element from cluster 1, and 1 and 2 are both in this cluster, and as an element from cluster 2, and B cluster has elements from all of these clusters. So then the Jaccard similarity between A cluster and B cluster is now going to be 2/3 instead of 2/6, because they share, the intersection is these two sets and the union is these three instead. So you can kind of layer stuff on top here instead. This allows you to do a bit more modeling on this sort of similarity by developing these clusters instead of these just individual values. You can also add this modeling in how you get these certain values, and we'll talk about this with text in a second. Okay, all right, so now I want to show an example with so first so the Jaccard similarity is pretty simple and clear to everyone, right? So let's see an example here with text. So here's a simple example with text here. So some of you might recognize this, and let me write out a small version of it. Okay, so what we want to do is to convert this into some way that we can use some distance as this distance as set. And so the simplest way of doing this is what's called the back of word of these documents, it's going to say, what are all the words in this document? Okay, and so the example with the bag of words would now be a set of these words. And so these have the same words in both of these documents. So from this sense, so once I have these sets, then I can use the Jaccard distance between these sets. So there's a slightly different way of, so this is the fairly simplistic model. You could also think of, remember I wrote up that there's this larger set n here. This could be like all possible words, and you don't want to have to consider all possible words when comparing these sentences with only three words in them. You want to only work with the words in the sentences, right? So, what's done in a lot of these situations, typically with bag of words, you do more than just the set. You actually convert this into vectors in Rn. And so n now is the set of all possible words. And usually instead of just keeping track of which words, if a word occurs twice, then you count it twice. So now each of these could also be seen as some point in some large dimensional vector space. Okay, so when I write something with the parentheses, this is then an ordered set. So if I write a vector in Rn, it should have n elements in it, and each of those elements should be some numerical value. So this is saying the first word in my set in 1 through n corresponds, with the word I. The second one was m, and the third one was Sam. So it doesn't matter what order they are. Maybe the fourth one here is like at or something else. It doesn't matter the order as long as I'm consistent across both of these here. And so I may have a predetermined idea of the order of these elements, and I don't actually have to specify an order. I just have to know which number corresponds to which word, and then I can treat these as vectors. These vectors, I can do things like Euclidean distance between these vectors. Often what you do is you normalize them so the sum of all the values, or the sum of the squared values is equal to 1, and then you can compute the distance. This is a little bit more powerful because if you have the word Sam occurs twice in this sentence, then you can, for instance, in document D4 here, the word I occurs twice, then I can have a number 2 here to say that the word I occurred twice. So it has more weight. And certain words will occur and more likely much more frequently than others. So you want to keep this into account. So this is known as the bag of words. Yeah?
So are those numbers the indexes, or are they the number, the frequency of the words?
They're the frequency. Yeah, so these are the frequency. The index is implicit in the notation. So you think of it as if I have a point in 2 dimensions, right? And so this is the x coordinate and the y coordinate. Then this is the value 2, 1. The x coordinate is 2, the y coordinate is 1. I could think of this in a much higher dimensional space, and I would need, in a n-dimensional space, I'd write it out like this, but it's much harder to visualize. We'll talk about high dimensional vectors later on in the class. So another question. Yeah. So I'm actually not going to talk too much about this bag of words model, although this is very common in some areas. They'll typically do more complicated things to compare them. There's this technique called LDA, which is this Bayesian, essentially a Bayesian technique of comparing documents. So in order to kind of get structure out of here, you can put much more high-powered things on top of it. It turns out it's very hard to tweak that technique to get it to work very well. But if you can do that, some people have shown some systems that seem to be very, very powerful, but it's very hard to use in practice, from my limited experience. Okay, so instead of this bag of words model, we're going to do something else, talk about something else called K-grams, or often it's called N-grams, but I like to use N for something else. And the idea is to kind of get more structure out of the text than just the individual words. Because here I had the same words, but they're, well, these sentences are really kind of saying the same thing, but you could imagine sentences that where these sentences are different, but I'm not capturing that in just the bag of words model. So the simplest version is the one shingles, where if I took, so I'll give some examples up here where I'm just looking at this as one single document. So instead of doing individual documents here, this is one single document concatenated together. I'm just looking at the set of all the individual words. This is almost the bag of words model, except I'm not counting duplicates. So Sam, which is in there 3 times, I only keep it in the set once. The set only determines whether it's in there or not, whereas the frequency vector can do counts. What's more interesting, though, is when you do something like on the K-grams, where I'm taking all pairs of consecutive words. Right? So the first K-gram, I am, is these 2 words together. I look at all pairs of consecutive words. The second one is am, Sam. Right? And then the third one is Sam, Sam. And then I have Sam, I again. But then I already have I am. Right? This is already in the set. So I don't have to put this in. So I am, yeah, and then am I is in there because it wraps around D2 to D3. Okay, so these are known as the K-grams. In particular, these are all the 2 grams. So you may have some questions. So there's some things that I've left out here a bit. So I didn't do anything. I didn't do anything with punctuation. Right. So there's I've not kept any of the punctuation. I've only kept the words. So this is a choice. You can add in the punctuation to have more complicated sense. This is sometimes useful. Before we go into this discussion, I also mentioned that you can also do K-grams with characters instead of words. Right? So this is a 3-gram with characters. So here the first one is basically the same. It's the first 3 letters. Right? And then the next one is AMS, is the next 3 letters grouped together. And MSA is then the third one. And then so I just did these for, this looks like this is just the first 2 documents, right? So the SAM occurs twice, I only have it in there once. And then here's another example with only 4 characters. Okay, so in doing this, there are lots of different options, right? I could have used, so for K-grams, there are lots of these options. There's using the words or the characters. There's do I include punctuation. So I didn't include any punctuation here. I could have done this. Another thing up here that you can see is the value of k. So kind of a rule of thumb on the value of k is that you want a pretty small, you want to have some collisions, but not too many. So if I use k equals 2, that's probably going to be, that may seem like it's too short, but it's actually for shorter documents, a value of k equals 2 or 3, if you're doing characters, is often pretty useful. So if you're doing something short like emails, so you want to do like 2 or 3. If you want to do longer documents, so say you're looking at like essays for people's homeworks they've turned in, you want to use a larger value of k, maybe between 3 and 5. And this is mainly for characters. So when I first saw this, I thought, when you're doing the work with characters, you're losing a lot of information here. So I'm not capturing, that I am is 2 individual words here. I'm kind of just squashing them together. And I'm not even getting whole words, like, because the characters are so small, I'm only getting these parts of these words. But if you're doing this, if you're going to use this for the Jaccard similarity, then the characters is really capturing this, because if you have the word green in there, well then if you're doing a thing with characters of 3, then you're going to have GRE, you're going to have REE, and you're going to have EEN. All of these 3 grams for characters in the set. And so you're going to be able to tell the similarity that way. So if you could have like 2 similar words like eggs and well, eggs isn't a good example. So like not and like note, right? So these are going to be different words, but they're both going to have the thing NOT in it. So this is a collision.